Right, so this talk is not about types. Okay, so please change your minds and switch over to JavaScript. As you've heard, on Monday, if you were here already, oh no, on Tuesday, sorry, JavaScript has conquered the web in the last 20 years. So nowadays you can say it's the language of the web, and 90% of all web pages are making use of it. Now, JavaScript programmers have a little bit of an interesting culture. So JavaScript programs are usually not written in one go, but they're composed of fragments from different origins. So clearly, a couple of those JavaScript fragments are ill-behaved, right? So for example, your JavaScript fragments, they may change the state of your system in unwanted, smelly ways, right? They may choose to expose your private state to the public. And they may corrupt your application data. So how can you guarantee that objects, and I'm using the dogs as objects right now, how can you guarantee that the objects behave? So our proposed medicine is one that you've already heard about in the morning and already in the last few days. So we would like to use contracts with runtime monitoring in order to guarantee that objects behave in certain ways. And that has a long history, meanwhile, over 10 years. So there are behavioral contracts that you've heard about today already. There's access contracts that we worked on a couple of years back. You can use security policies regard them as contracts, and you can also use membranes as proposed by Van Cutsem and Miller to preserve data integrity, for example. All right. A very useful implementation technique for contracts that's also proposed for JavaScript by Van Cutsem and Miller is using proxy objects. And indeed, there are implementations for contracts for JavaScript by Disney and Flanagan and by ourselves, relying on proxy objects. And essentially, the idea is that, you can see something maybe. Suppose you want to guarantee that your target behaves in a certain way, or that your target down here, that your target's integrity is preserved in a certain way. Then you introduce a proxy object. You essentially introduce an indirection, and the nice API provided, in ES6 actually, allows you to redirect usual object operations on the proxy object and translate it into method calls on a handler object. And the idea then is, instead of your target, you use a proxy that interprets many operations on the target, and then use the handler to implement whatever the contract says. Yeah, and all the things that I showed you on the previous slides are, well, it's applicable to all of them. Yeah, so there are implementations that use that. Well, unfortunately, here I put a footnote on the all, and I'm reading it because the last line is invisible for many of you. Some of the operations actually resist. And there are reasons for that, and I won't go into that. Right, so let's now look into a particular way of using these contracts. And this morning in the first talk, I realized that we were on a good track because Asumo already quoted Matthias Keil, that he said contracts are good to empower programmers. So the idea of using contracts is to empower programmers so that they can gradually enrich scripts with types as they perform maintenance work on their system. Let's switch to maintenance mode. Okay. After midnight, you're hunting some bugs, right? As we are all disciplined programmers, we do it by adding contracts as our understanding of the program dawns, right? Maybe it's 4 a.m. already, so there's really dawn. Right, and as you're adding contracts, so the program is going to execute in a mix of objects with and without contracts. So that means the same object may actually appear in your state once with a contract and once without a contract. Or it may even appear with different contracts applied to them. And that means, in the worst case, that the naked object may be compared for equality with its contracted counterpart, or two differently contracted counterparts may be compared to one another. Now the interesting question is, what happens, right? Yeah, so 4 o'clock in the night, you drank lots of coffee, Red Bull, or whatever you used to stay awake. Yeah, so what happens? Let's try it out. So up here, there's the original object, right? Now, someplace in your code, put a contract on it, and right here, I'm making this is a fairly abstract example, so you put a proxy on the original with some contract handler, and what you find out, they're different. But initially, before you inserted the contract, they were equal. Similarly here, so here I'm using the same original object, I plug another contract on top, and again, they're different. Yeah? So if I have different contracts applied to the same thing, they're different. So the consequence is, if a program uses object equality, then adding contracts may actually change its behavior. Yeah? So during the maintenance phase, where you're in pursuit of some bugs, you're using something to hunt down the bugs, and it changes the behavior of your program. Now you may ask, and I think I've been asked that, does this really happen? Yeah, this is certainly an academic question, right? Does it happen? Okay, so I have two answers to that. Answer number one is, well, I can construct a concrete example where it happens, right? So let's take some contract T that's implemented by a proxy. Yeah, for example, Sumo demonstrated objects contracts. These are perfect. They install a proxy on top of that. And now let's use the macro view that Sumo also used in the first talk. So we consider a module interface which has just one exported function, foo, with a contract like this, T arrows any, and then T, and then it returns any. Yeah, so it takes a function from T's to something and a suitable argument for this function. So right, I don't want to go into the implementation, but nevertheless, the implementation of the contract applied to foo is some wrapper object that asserts the contract. And we'll see what it looks like in a second. So now consider an external use of this foo module. So we might create some object, that's the x here. Now we might create some function that takes an argument and compares x and y. So the important point here is x is a free variable that lives in the closure of the function f. And now I'm calling the wrapped foo with f and x. At this point, I have to reveal what the wrapper actually does. So what the wrapper does is this. Maybe you don't, sorry, I can't scroll it, but then you'll see the next point I want to make. So the last line actually corresponds to the following. So the function argument f here is going to be wrapped in another function. You could say a proxy, and you could implement it that way, but maybe this is easier. So it takes the actual argument, and then it calls f with the contract for t applied to the argument y. Now that's the standard Findler-Verleisen implementation of this t to any contract. Yeah, and I'm dropping off the return value part because it's any, and it simplifies the code. Similarly, the second argument, which is probably invisible to many of you, that just wraps x, the argument, in the proxy that handles the t contract. That's just standard Findler-Verleisen stuff. Now, if the module implements foo by just function application, right? So if foo is just, and now I can actually, if foo is implemented, foo of f and y is implemented as return f of y, then the call of wrapped foo returns false instead of true. Right? Is that enough?
Yeah, one more.
One more. Yep.
Okay.
You good? You don't know. So essentially what happens, I think this is all the essential information. Here I have an object that's captured by the closure of f, and then in the body of the function, I'm comparing this captured thing x with the argument y. And now this function in this example is constructed such that the argument is certainly wrapped in the T contract, right?
No, I'm not good.
Maybe wait until the end of the talk.
Yes.
Okay. All right. So, but it should be clear at this point. So x is a naked object, and when y reaches this point here, it's going to be wrapped in at least one proxy that implements the T contract. For that reason, the application, the function application here, the equality check returns false. But if you look at the original function and if you ignore all wrapping, then it should return true. All right. So now you could say, this is an artificial academic constructed example, and this never happened in practice. Okay, so research question number 1, does it happen in practice? So we performed the following experiment. We instrumented a JavaScript engine, to count and classify object-to-object comparisons. Then we applied this engine to mutants of Octane benchmarks programs. So what was the mutation that we did? We wrapped arguments of randomly chosen functions in a membrane. A membrane, so we had that, So a membrane is something like a recursive object wrapper that expands on demand. So initially you just get a proxy to the object, and when you access, then you create further proxies that keep the wrapping around this object structure as far as it is explored. Now, the most useful variant of a membrane is an identity-preserving membrane, and it preserves aliasing. So when you wrap the same object twice during the recursive construction, then you return the same proxy. That ought to be expressed by the last line, but it was late yesterday. Now, we looked at the data and we classified the object-object comparisons in 4 categories. So the first category, so there are 2 major and 2 subcategories. The first category was comparisons of this kind, where I have a wrapped object compared to a naked object, or 2 wrapped objects where the wrapper originated from different membranes. So M1 and M2 are supposed to be membranes, and they're different. Okay, so now we distinguish 2 cases, namely whether or not the underlying naked objects are equal. Are same, right? In the most restrictive sense of the word. So if they are different, then the result should be false. Okay, and that is going to happen in all cases. So these cases, they don't matter. They never change, regardless how you implement your membranes. 1b. So if T1 and T2, so the underlying truth, are the same, then this result should be true, as in the example that I demonstrated you. And this doesn't come out this way with JavaScript proxies. So with JavaScript proxies, it's false, because here the membrane, the proxy, has a separate identity, which is each proxy is a new object which is different from everything else. So M1 of T1 is different to T1, and similarly M1 of something is different to M2 of something. So at that point, if you see 1b cases, 1b comparison, then these are programs that change their semantics. The second case is you have the same, type 2 is you have the same membrane applied to objects T1 and T2. And again, there are 2 subcases. First of all, if T1 and T2 are different, then the result should be false. Okay, and that turns out to work for all implementations. And again, the interesting case is T1 equals to T2, in which case the result should be true. If membranes are identity preserving, that's going to be the case. If you were not careful in implementing them or ignored it, then it's going to be false with JavaScript proxies. All right, now let's look at the measurements. So these are 4 benchmark results from the 4 benchmarks from the Octane benchmark, and you see here there is ample stuff inside of the 1B case, which is the bad case. So it happens. That's the short message. Now you may wonder about the remaining 20-something programs in the Octane benchmarks. I should have edited it. They don't do object-object comparisons that can never be affected by proxies. So they may do naked object compared to naked object, but we don't. We have the numbers, but I don't have them in this table. But they don't do any dangerous things. So it sometimes happens, but it does indeed happen. So what's the medicine? We have some proposed medicine, of course. Our proposed medicine is to use transparent proxies. The idea of that is when you compare two objects for equality, then a transparent proxy is recursively replaced by its target object, whenever you do this. And the suggested use is to implement contracts that behave like projections with such transparent proxies, or membranes as well. And these contracts, in that way, become invisible for object equality. And it would solve the problem for all these benchmarks, because, in fact, we've run them with a suitably modified JavaScript VM, which was why we could actually run these benchmarks to the end, because if you change the semantics, then some of them will just crash. So they're invisible. The implementation, we did the implementation in the SpiderMonkey engine. So we changed not all of it. So we changed changed the interpreter and the baseline JIT compiler, and essentially the change is conceptually the change is on this slide. So we had to change the definition of object equality, which is one part, the seventh bullet point in the abstract equality comparison algorithm, which says return true if x and y return to the same object. And this has to be replaced by, get the identity object for x, get the identity object for y, and then return true if both of these refer to the same object, and otherwise return false. So as a side remark, there are, in recent versions of JavaScript, there are also maps and sets and weak maps. And as these also rely on object identity, they also have to be changed accordingly. Where accordingly is not quite trivial to define, but see the paper. So these have to be touched as well. So GetIdentityObject, I'm using pseudocode or JavaScript syntax, but in fact, of course, the implementation is in C++. But you can't read it. So essentially what it boils down to is a while loop. So you check whether it's a proxy. If that's the case, then you check whether it's transparent. And if that's also the case, then you replace it by its target. And getProxyTargetObject is a method that's already present, as far as I remember, in the implemented proxies. So this little loop is all that has to be added at the right places. Okay, now you've messed with the JavaScript virtual machine. That leads us to question number 2, right? So if you extend equality, how does that affect the performance of programs that don't make use of proxies? So if your programs now run a couple of percent slower, that wouldn't be a good idea either, right? So again, we turned to the Google Octane 2.0 benchmark suite, and we made experiments once with IronMonkey turned off. This is obligatory because, we didn't implement our extension in IronMonkey. That's the highest level bytecode compiler. And we also turned the JIT off, which means we have experiments with just the interpreter and just the baseline JIT running. And then we performed one run with the original VM and one with the modified VM. And there are flags so that you can turn things on and off nicely. And here are the results. Essentially, here on the left, you see origin, that's the original implementation. You see transparent, that's the implementation that extends the equality operator in the way that, that I've shown you. And if you compare the numbers, which should be easier to do in the paper, or here if you look at the total score and summary, you see there's not much difference. And in fact, the difference is within the measurement inaccuracy. Yeah, so if you run the benchmark a couple of times, then you have small fluctuations in the numbers. And here you see, well, here you see, for example, for the, this is already compiled code, so it's less than 1%. And which is actually within the usual flotation of the Octane scores. What's this? Okay, yes. So essentially, the difference between original and transparent is within the range of measurement accuracy, which to the best of our knowledge means there's no measurable difference. Now, one thing that's not in the paper and that I don't have on the slide, we essentially, we also had an instrumentation run where we counted all equality operations. And we found that only a tiny percentage of the equality operations actually boil down to object comparisons. Yeah, so you need a logarithmic scale to even see the bar for the object comparisons. And of those only, and there are many programs that never do any object-object comparisons. The most frequent comparison involving objects, it's actually to compare objects against null. That's the most frequent thing. All right, so we're almost there. Just to show you the flavor, the user level API is very simple. We just have a new proxy constructor, but that doesn't solve all the problems, so there is a little additional twist. The thing is that transparent proxies are a little bit slippery, right? So if you want to manipulate them, yeah, so you want to write code that somehow performs manipulations, so you want to build a library that uses proxies and does something interesting with them, so they're kind of hard to manipulate because they don't have an identity. Yeah? In some places of the code, you may actually want to see those guys. So how do you do that? So the solution is to use something like capabilities, where you create an identity realm, which means you create an object that serves as a factory for providing an object constructor and an equality that goes with this particular object constructor. And the idea is that this equality that comes paired with the proxy constructor, only this equality can tell objects transparent proxies constructed by this constructor apart. For everything else, for every other equality comparison, they're equal. And this little code fragment is supposed to demonstrate. So here, transparent proxy create realm that creates such a equality realm, and then you can create proxies in that realm, and you see they have the same target. So then outside P1 and P, well, this is obviously always true, so this should be P2. Well, outside P1 is equal to P2, because, well, they are transparent proxies. But if you use the equality inside of the realm, then P1 and P2 can be distinguished. Right, in the paper you can see another API for creating transparent proxies, but we think this one is more intelligent. We also make a proposal for observer properties that guarantee that, that a contract implementation is always a projection, so that you can safely use transparent proxy to implement them. We also have a discussion of the specification of equality, which is maybe a little bit philosophical. And we have discussion of a couple of further use cases of transparent and opaque proxies, where opaque are the ones that are distinguished by equality, the standard JavaScript proxies, let's say. All right, and that brings me to the conclusion. Implementing contracts with opaque proxies as it's the current state in ES6 changes the semantics of contract-abiding programs. We suggest that transparent proxies are a viable alternative. So our implementation demonstrates that it's readily implementable. We couldn't measure any performance impact on programs that don't use proxies. And from our view, it seems suitable for all the existing use cases. So to preserve programmer expectations, transparent proxies should be used as observer proxies. And this is a similar distinction as between chaperones and impersonators in Racket, only that, so observer proxies should be analog to chaperones, only that they behave differently with respect to the low-level equality. There's still something to do, all right? So I mentioned we got up to implementing it in the bytecode compiler, so there's still IronMonkey to go. And yeah, we would like to gather support. If you would like to see this implemented widely, of course, you can fork from our GitHub repository, which is mentioned in the paper. And otherwise, well, yeah, thank you.
Hello, hello, okay. So I have two questions. One is that because you're wrapping the membrane around a module, how is it that with the foo F slide, how is it that something on one side of the membrane ended up with access to both the naked object and the wrapped object?
All right, so I've used the membrane as a simple example for a contract. So essentially, I'm expecting just a contract proxy at that point.
I did not understand the answer.
Okay.
Especially in the context of the benchmarks, where you said you were wrapping them around modules. How is it that you saw failures? Because if you're wrapping them around a module, fully wrapping it, then there's no object that should be able to appear on both sides of the membrane.
I think you have so the thing is that the membrane is only wrapped around the arguments of the function, but the function itself can have as the function is passed as a parameter, but the function itself has a free variable that contains the object unwrapped. And then I'm passing the object in again, the same object that's also captured in the free variables, and then inside of the function body, the wrapped thing and the captured identity, they come together.
Okay, and my other question is,
and I'm not using the let's say the intended semantics of the membrane. Maybe I should just have said I'm using a proxy there. That's,
okay, so my other question is very fortunate that this talk came right after the talk about brands. The purpose of a brand, going back again to James Morris in 1973 and all the work that I know of since then, is that the nominal type it represents provides a assurance that some behavioral invariants are satisfied, that anything that passes the brand must behave in a certain way because, for example, it came from a lexical scope where the brand was available, and therefore only things that were known to behave that way were branded. It is already the case in JavaScript that people are using weak sets and weak maps for branding. Is it not the case that with equality extended in this way, including extending it with regard to lookup of keys in weak sets and weak maps, that one can build objects that pass a brand check but violate the behavior that was associated with the brand?
I think, and it's still here on the slide, I think the recommendation is that you should only use transparent proxies to restrict the behavior of an object by way of a projection, so that you can remove some behaviors and replace them by error messages. So I don't want to change the behavior of the object. I want to restrict it, but I don't want to change it.
The point is the adversary can create a proxy. in order to create an object that passes the defender's brand check but violates the behavior that the defender had in mind. The defender never needs to use a proxy at all. He's just using a brand check to assure that objects that pass the brand check have the behavior that they designed.
Well, okay, but as far as I understand your scenario, you still need an underlying brand object that has been passed around by the original.
The brand object is just a wrapper around a weak set or a weak map doing an identity check.
Maybe this is something that we should discuss offline because I don't understand all the ramifications right now.
Hi, here. Excellent lucid talk. I love the talk. Had a question and a half regarding the evaluation. Mm-hmm. So you disable the optimizations. And I'm actually starting to think that because the optimizations are disabled, you are getting a performance that is looking very comparable. See, when I have, say, inside a loop, an object comparison, it is just an equality. Mm-hmm. And no branches, nothing. The compiler can move the code around and do a lot of optimizations. And now you replace this object comparison with a complex function call and get the function results with a loop and all that. The code cannot be moved. So as a result, I'm afraid that if you put the optimizations on, the difference between the execution time of the transparent proxies and no proxies can be significant. What do you think about that?
Okay, so as far as I understand your question is if we also implement this for IronMonkey, you would expect bigger differences. I think that won't be the case because, as I told you more or less offline, we also have numbers about the total, about all comparisons. And the number of object comparisons is just a very, very tiny fraction of all of those.
Wherever there is comparisons.
And the nice thing about about an engine like SpiderMonkey is that it performs some inference and some type inference, and therefore it knows most of the time that something will never be an object. So this test will never even arise in the code. Yeah, so only if it knows this, it could be an object comparison. Only in these instances the code would actually generate it. And then this thing would be this would be inlined in the places where it can infer that an object comparison may take place. So I suspect, well, this is guesswork, right? So I think the impact wouldn't be large, but it would have to be tested. I don't have a hard answer.
So I'd love to see this change to JavaScript, but as long as Mark opposes it, I think you and I are in trouble, so we better team up on him later.
Let's do that.
I just want to add to your evidence that this is a problem in practice. I have a student, Jack Williams, that was looking at exactly this. His methodology was slightly different than yours. He took the definitely typed repository, which gives TypeScript types for modules. About half of them have test suites. So he just built a wrapper that imposed a check for the type given by the TypeScript declaration, and then checked would it still pass the test suite. And the answer is in about a quarter, it doesn't. And very often the reason for that is this problem with equality that you identified. So further evidence that's a problem in practice.
Thank you.